is I've taken a number of lectures that I teach at Berkeley, and I've added more material. I've kind of massaged them to make them, I think, appropriate to this kind of audience. And some stuff you may know, other stuff you may not know. The other thing I'm doing, and we're going to go for maybe 2 hours with a break in the middle. That's my plan. But I feel I'm really excited because I prepared the project for you as well. I think just listening to me is not going to do you much good. Not that I'm not interesting to listen to, but we're going to sit down and do a project at the end after my lectures. Okay. So this is about automated testing. The audience are developers who are interested in writing any kinds of code, because I think you should be writing tests when you write code as well. I brought with me a textbook that I use. It's a good reference book. I'll just pass it around for you to look at. And I have some citations to this book. This is the Messer's book, xUNIT test patterns. As you can see, for something that's as simple sounding as xUNIT, or it's a very thick book because there's much to learn. I'll just pass it around for you to take a look at. I think we used to have one in Conviva around, but I don't know what it is. Okay, moving along. Let me first talk about test automation, because I really think tests should be automated, and if they're not automated, they are a different kind of beast altogether. And if you don't believe this already, the reason I'm saying this is because if you don't automate them, you're not going to run them often enough, because it requires a human. And if you don't run them often enough, they'll rot. Okay, because code rots. And pretty soon, you'll move on to another project, or your brain will move on somewhere else, and you will forget how to run them, and then the tests are actually lost. So if you automate them, the automation is going to keep you honest. It's going to point out, in small ways when you have to change it. Furthermore, so this is the first part of automation. They should initiate themselves and execute themselves automatically, but they should also verify themselves automatically. And this seems like such an obvious thing, but when you write tests that fail 2% of the time, 5% of the time, that implicitly means that there's a human who has to go in there and think about why the test failed. So that's not a fully automated test. Okay? Now, this is hard to do, and I'll be the first to say that. Sometimes I actually enjoy writing the test more than writing the code, because sometimes it's harder to write the test than to write the code. Somebody could be giving you a boring programming task, but testing it is actually the interesting part.
So question, so in terms of hard writing a test, you mean hard to design the code so that it's testable, or it's hard to run the test?
Everything. Hard to make the code testable, hard to write the test, hard to do the verification. Everything could be hard. Okay, and there's one, I want to just bring in my first lesson of the day, something I've learned the hard way. One of the biggest enemy of testing is trying to test too much. Okay, this seems like a strange thing to do, but my biggest success in testing has been when I scaled down my ambitions of how much I want to test. And I've written some tests here in the past 9 years that were really very ambitious and says, well, you should test that and that and that, but that might be just too much. And instead of having a test that passes 99% of the time, maybe you only test, drop by 10% your ambitions, and you have a test that passes 100% of the time. And that's more valuable. Okay? This is hard to get across. Some of you are already looking at me strange. There's another enemy that's perhaps more obvious, is the mentality that I'll do it later. Okay? This does not work. So let's be honest. Okay? If you were to build a car and say, I'll think about testability later, how will you measure the level of oil? You'll have to drill in the engine, because you haven't thought about that. And to change the oil, you'll probably turn the car upside down, because that's the only way you design it for the oil to flow out. Okay? So you have to do testing from the moment you design the code. And this is something that it's incredibly hard to get across. I'm trying to teach my students who are still in school, and they look at me like, this is like my parent who says you should eat broccoli. It's good for you. I don't believe that. But hopefully you'll believe it more easily. But test automation is not a panacea. It's not solving all your problems. In fact, if you do it badly, it's actually going to drag it down. So here's kind of a qualitative view of the cost over time of developing code with or without tests, and with good tests and bad tests. So initially, over time, you have the initial development. This is when you are actively vested in this project. This is the only thing your brain is occupied with, even when you sleep. So you have a good control over your tests. You've set up your desktop to be able to run this code that you're developing, even if you're not thinking of testing. Then you release, and then you go into maintenance, which is much longer than the initial development. And this is how it goes if you don't do tests. In the initial development, this is kind of the slope is how hard it is, how much effort per unit of time you're putting. And the interesting part is that even after release, you find yourself being just as busy, because now you have more code. You're writing fewer features, but you have to worry that these features work in the context of this code that you've written. And then here comes the refactoring. And if you've been involved in a project years, you know that this will come, this refactoring. And it's scary to do without tests, because you don't know what you're breaking. And I'm even considering that it's you from the beginning to the end, like I've had the fortune to do here. But often you get assigned to a project that you haven't written. So refactoring is even scary. So how is testing going to help? Okay. Sorry, my animation is behind me. So refactoring is very hard. You see big jump in cost when you're doing refactoring. And this is what you can hope with automated tests. You're going to be investing more from day one. And as you write code, you invest more. The hope is that once the code is mostly done, then as you write little code, you have very little verification to do, because the tests that you built here will help you. So this is how you should hope the maintenance to be. So really come in tactically, fix a bug, run the test, know that it's all working, deploy. Okay? Refactoring is still going to cost, but at the first refactoring, sorry, I have too much animation here. At the first refactoring, you're ahead if you had tests. Before the first refactoring, probably your investment is bigger than you'll be able to read. But at the first refactoring, you should be ahead if you've written the test properly. And then you still go on with relatively lower maintenance cost. And it's hard to kind of reflect this on the graph, and it's all qualitative. But believe me, I mean, in projects like Touchstone, for example, which runs in production, somebody can come to me, I can fix a bug, I can all deploy it in half an hour, okay? With what I think it's a full QA run. And then I can move on to whatever I was doing before they came to me. That's what I mean by low cost. But you can be perhaps doing tests badly. And when you do tests badly, not only do you pay for building the tests, true, the refactoring is going to be better, but the cost of maintaining the tests, if the tests are bad, may be just as high as if you didn't have them. So, and this is one of the, there are many ways to write bad automated tests, but for an example would be tests that take a long time to run, tests that fail often, tests that involve many moving parts that, everything there's something to maintaining them, and we have our own share of those tests you may know about. Okay, any questions about this? Economics of testing?
So are you going to talk about what is a good test, what is a bad test? And,
You're anxious, yes. Yes, I will. I will. To a certain extent. Okay, moving along. So these are obvious things. The tests should be repeatable. They should run all the time the same on your machine and on the automated build machines. They should be robust. When the test fails, it should be for a good reason. Sometimes a bug in the test, but when it starts failing, it should fail every time from there on, because that will allow you to fix it. Now, tests that fail 1% of the time are not very useful. This is another big thing I didn't appreciate a long time ago. Tests should be fast. The first test I wrote here, they were now playing video at the video speed, and they would go on for minutes. And they would have these sleep statements in there. Let's wait for 2 minutes or maybe 3, because until something good will happen. Those tests are not that useful. I mean, if that's the best you can do, fine. But What I believe now is that I should be able to run the test in a stretch break. For something as big as Touchstone, it should be a minute to run all the tests. Okay, how you get there, that's part of what I'm going to talk about next. So let me start with unit testing, which I believe most of you have used. I will just review it briefly. Hopefully it's not too repetitive, and then I'll go on to something, an angle on unit testing that's interesting. I do want to give credit to Kent Beck here for xUnit. You might not know the history of this, but he created xUnit for Smalltalk in 1989. And this guy has done a lot. I mean, he's part of the, okay, I'm kind of blanking now, but I'm blanking on exactly everything he's done. But I think he's string programming. He's the extreme programming guy. He's one of the agile programming initiators, and he created xUnit. Once Java unit testing library appeared, the framework took off, and pretty much people implemented it for every language. So there are about 70 of them listed in Wikipedia. Yes.
Sergio, are you planning in your session to kind of cover the link between unit testing and testing as a whole with the release methodology, like agile versus waterfall? Or not?
No, I'm not going to go to agile versus waterfall. I'm going to go beyond unit testing, but not. I mean, this is, I should say, I'm teaching a whole class of 30 lectures here. These are about 3 lectures compressed. If you like it, we may do more. The nice thing about xUnit is if you get a language that doesn't have one, you can build one. And in fact, we have built, for a few of the languages that we use at Conviva, we built the testing library ourselves because there wasn't one. And I like this quote by Martin Fowler, which is another big name in software engineering. Never in the annals of software engineering was so much owed to by so many to so few lines of code. It's really very small, and it does a lot. So again, the textbook that I passed around describes a lot of this. Let me introduce some terminology, mostly so that we have a common vocabulary for the rest of this lecture. I will be talking about the code we're testing as the system under test, and I'll abbreviate it as SUT. And it's important to realize that very often, to run the part of the code that you want to test, you need to involve other parts of the code just to have it running. However, so both of these are part of your production code, but the focus of the testing is on this one for a particular test. And then maybe the focus will switch. It's important to keep this in mind. This is the object of our testing. This is, I'm going to call it as a collaborator or a dependent on component or a doc. Okay? We'll be talking a lot about these two. These two together are sometimes called a text fixture. And sometimes that may include the actual input that you need to pass to the system under test to run. But okay. So this is the code that we're running, and then a little bit about the tests. Tests in the xUnit test framework are organized into test methods, and the test methods are collected into test cases. Okay? And every library for every language has slight variation in this, but this is the general idea. So typically you'll put several test methods that share the common setup into the same class, and you'll write one setup method for the class itself. Okay? Any questions here? So, yes.
Related to this. Is this like a videotape or something?
It's recorded.
Oh.
It's not live, but I'll be adding in smiley faces afterwards. Okay, so let me just quickly go over what happens in a unit test, because there's some delicate things for those of you who haven't used it a lot. Okay, so this is the testing library that you typically download from somewhere. This is the class that you write. This is where you put your tests, okay, your testing code. And the testing code is organized into tests that run in sequence, typically. So what happens when you start the test, you create an instance of your test class, and then you call this special method setup. This is a method that you write in this class to kind of create a few objects that you'll be operating on. One of the things that setup often does, if your tests require a collaborator, is to construct the collaborator or to start the collaborator. This may be a database that you initialize, okay? And it's not what you're testing, but you'll need it for your test. And then the test will actually construct the system under test. This is an instance of the class whose method you're testing here, let's say. Okay, and that ends up the setup stage, and then comes the actual test code that you write. And in the test, you typically make some calls to your system under test, which will probably use the collaborator in some way. And I do want here to introduce another terminology that I'll be using. This is the system we're testing, and you may think that these are the inputs. When you call it, you pass it some inputs. And then it gives you some outputs back. But those are the direct inputs and outputs. This thing, if it uses an external API, a database, or a web service, it's going to have additional outputs that you may not see, because they go from the system under test to the collaborator. But that's technically an output of the code you are testing. And whatever comes back from your web service that you're calling or the database, that's an additional input. Okay? And then your test may actually say, okay, you exercise it, it does its work, and then you go probe it to see what kind of state it is in, and then you're doing assertions based on the state that you're testing, and then that kind of terminates the test itself. Now, it's important to realize that typically you write this part, you worry a lot about this part, what assertions you're going to do, but very often we're missing to observe what happens when this code makes its own request. So imagine that you're testing some session summary computation, and you're passing in a heartbeat, but it's going to go get the session summary from the previous heartbeat from a database, and it's going to update the database somehow. And who knows, it may even be requesting something from Conviva or some other services. Ideally, you should really view all those as inputs and outputs. One more thing I want to point out here. There's a counterpart to setup. There's a teardown method that's very important when you write tests, because this is the method that actually cleans up after your test. And cleaning up the system under test sometimes is not as important, because you're going to create a new one when you run the new test. But what's very important is to clean up your collaborators, if you're using collaborators that have external state. And those of you who have worked on web apps, for example, and you think of depending on collaborator being the database, you know that you need to really worry about initializing the database and cleaning it up, because if you don't do that, future tests will actually fail just because they are running into a dirty state. Yes?
Should we actually run assertion on the DOC?
Should we run assertions on the DOC? Yes, and I will get to that in a few slides. We should run assertions on whatever the state, and we should run assertions on these as well, on the outputs.
Where do you set up the dependency?
Say it again?
Where in the diagram do you set up the dependency?
The dependency would be set up here in the setup stage, when you actually construct the dependency, construct the system under test, and somehow you have to connect them. That's called dependency injection, and that's actually at the end of my slides for today.
How to handle the parallelization?
The what?
Parallel. For example, you have double test cases. You don't run the second one. So how do you run parallel?
I'm not really describing here how you parallelize this, but if these tests are really independent, I mean, if there's no dependency between them, you could run them in parallel if you have enough resources. But I'm not really going to go into that.
So we can mock the DOC if the DOC is hard to...
Yes, we're going to talk about mocking quite a bit today, about mocking DOC. So you're kind of going ahead of myself. Maybe I'm too slow. We move on. So I'll go briefly about this. Just a few points here. This is how one test looks up the setup stage of one unit test, and this is for testing a vector class. The vector class is a good class to do unit testing because it doesn't have dependencies. It's at the bottom of your dependency chain. So all you need is to give it inputs and make sure that it has done the work. So it's kind of the easiest thing to test. I like to organize my tests such that they start with the name of the class I'm testing, because this way in an alphabetical listing of my classes, the test kind of fits close to the code I'm testing. Other people do different things. They call it test vector, whatever. The other thing that I think is very important is some people think that when they write tests, they should really have complex values, complicated numbers, just so that they test it better. I like to use very simple numbers, very recognizable values in my tests, because when the assertions fail, I like to know that this is the third element of my vector and such. So, and I really see, especially in the interviews that I do, I'm asking people, how would you test this? Say, oh, I'll write the vector with 1,000,000+1 elements, and I'll put random numbers in the vector, and then I'll sort it. And then, yeah, well, how are you going to tell, how are you going to debug this vector with 1,000,000 random numbers in it? So don't try to be too ambitious, because most bugs you can find with simple, small inputs, small data. Typically, you should have one method for the one test case for each method you are testing, and so each test will have some more code that sets up the method you are testing, and then a bunch of assertions. Typically, that's how tests typically look. Okay, and you may want to. This is the testing the clone method of the vector. You may want to have multiple tests actually for the same method to test different corner cases separately. But this is a rule I often personally break. In fact, purists will say that you should not have two assertions in a test. Do you know what's bad having more than one assertion in a test?
The second one will not run.
The second one will not run if the first one fails. All right?
Not using expectations instead of assertions.
Okay, yeah, you're going ahead too. So with the right kind of mechanisms, so that's actually a valid problem. But I will tell you about the bond library, which is an alternative way to write assertions that actually gets rid of this problem. So the reason, what would be the reason to have many assertions in the test?
So it's technically one atomic state, and you need to assert many properties about it.
Right. So you get to share all the setup, all the exercise code, and then you have more than one thing to verify on the result. So it kind of feels naturally that you have it all in one place. Some of the things I'm teaching you, others will come and say, no, that's really bad, really bad. So I'm telling you, they will say this is really bad, but it's not always black or white. Okay, so let's get into something a little bit more interesting now. And I'll start from this test capacity class, which what it does, it actually starts with this full vector, and it adds 100 new integers to it, and then it checks that the adding elements has worked. Okay, well, adding an element to a vector does many things. This test, all it does try to assert is that the size has grown by 100. So if you think about it, it's a very narrow verification. It's a very unambitious test, because you could be checking that exactly these integers are at the end, one after the other. All that would be testable. Okay, so a small thing I want to teach you here. Do not use assert true. This is really a detail. Assert true will compute the two sides of equality, and then if that's true, everything is fine. But if that is false, it's going to print this very useful message. Expected true, but was false. Okay? And if you get this in an email, because this test ran overnight, you can't really tell, except perhaps from the line number. Say, okay, well, clearly I either have too many or too few elements. Maybe I'm off by 1, maybe I'm off by 1,000. I don't know, so I have to run this in a debugger. So, so smart testers use take advantage of the richer set of assertions. And if you look at all of these xUNIT, JUnit libraries, they have about 50 of these assertions, so that you can use the one that's most appropriate for you. So assert equals is one of the most commonly used assertions. And this has the advantage that it will do the same thing as here, but it's going to be able to print a nicer message. Okay? Expected 103, but was 102. So even before you go to debugging, you kind of know what the bug may be. Okay? You missed one element. You have one too few. To use it properly, you should put here the first argument should be the expected value, and this should be the actual value, because the messages are printed with that kind of a thing in mind. Okay? So I assume everybody knew about the assert equals. okay? But don't use assert true as much as you can. Yes.
Oh, okay.
No.
I was going to say, I mean, there's cases for using assert true if you're asserting on like the output of a method that returns a boolean, like contains, for example.
Yes.
Okay.
Sometimes it's the
Only option.
only option, but some people use it because you can actually write tests with using only assert true, and that's not right. Okay, so now we get into something that I hope is going to be new for most of you. Sometimes I feel the need to write a lot of assertions because this is testing a binary search tree. It's in Python. I'll be giving some examples in Python. And this you may have seen on the Bond documentation. The inspiration for this was my daughter. She's taking the data structure classes. And so you spend all this time to insert a bunch of trees into your binary search tree, and now you want to assert that the insertion has worked. Well, you could assert that the tree has 5 elements, but that would be so shallow. I mean, it could be so many bugs you're not catching by this. So you might be tempted to write in things like this. I'm going to assert that all of these 5 elements, not only they exist in the tree, but they exist at a particular location in the tree. Okay? And but this is tedious to write. Okay? It's not only tedious, it's not even complete. If you want to really check that the tree is how it is, you should check about the missing nodes, like the null pointers. You should check that 6 is a leaf, for example. And you're not doing that because you'll get tired, of course. What's even worse, and you may not realize until you use this code for a while, is that if anything changes in your system under test, or the test itself, let's say you need to decide that you need a slightly different tree for this test, and you make a change here, well, that's going to change all of the nodes in the tree. It's going to be a mess to maintain the test. And it's going to say, oh, I'm spending all this time wasting my time with testing. So if you do change something, you're going to get messages like this. Assertion equals failed because 4 is not 7. Okay, so now you have to go in the tree and figure out what has happened. This is more common than it seems because if you try to be ambitious testing a lot of things about the behavior of your code, those assertions will have to be maintained as you change the code of the test. So either you test very little, and then perhaps the test doesn't need to be touched for months, or you test a lot, or you assert a lot, but then when you refactor the code, you may have to change it. When you change the spec, you may add the field to the database. You have to make a lot of changes. So this actually can happen a lot. And that's why about 5 years ago, while writing Watchtower, I had the idea of a way to fix this. So we created this library called Bond. How many of you have seen the James Bond movies? Yeah, you're young, I guess. I grew up with them. And he has, in every movie, he has this scene. So he's a spy for the British government, and very classy spy. So it's my name is Bond, James Bond. So that's where the name of the library comes from.
Which one is your favorite actor?
That's a long debate. I've read so many posts about that. I'm not going to go into that. I like the movies more than the actors. I grew up with Roger Moore.
Oh my
He's gonna walk out.
Okay, so here's what Bond does. Bond is assert equals on steroids. So the test is just as before. Okay, you set up the tree, and you exercise the function you're testing. However, instead of writing that, this assert equals that, I'm going to spy the values I want to assert on. So what Spy is going to do is going to take the tree, is going to serialize it to JSON, and it's going to save it. Okay? It's really like printf, like logging, except it's done in a specialized way. So this is what Bond is going to save behind the scenes for our tree. It's going to say, this is a spy point test at 1, and this is the tree. I gave this name when I spied. I say this is a tree, and it then serializes the tree to JSON. Interestingly, with careful to have all the keys in sorted order and 1 per line, because you want this serialization to be deterministic. Every time the test runs, it's going to produce the same serialization. And then the secret is to save these along with your code. The first time you run the test, the idea is that you're very invested in it. You're going to debug it. You're going to check it. You're going to verify that the test runs correctly. But then you just save the whole output of the test. Next time you run the test, in all future runs, this file will be saved in the temporary file, and then there's a diff done with the all. And if there's no differences, then the test has passed. And this implicitly has asserted that the data in the root is 8, the left data is 3, everything. So it's one line to write many, many assertions. So you're saving a lot of writing, but that's not the big advantage. The big advantage is what happens if you need to change these assertions. Because now, imagine what I've done. I've taken the assert equals from before, and I'm keeping in the test the first half of it. I'm saying, I care about the value of the nodes in this tree. But I'm not committing, I'm not writing in my test what the values should be. Those get saved on the first run into a file. So I'm separating the actual thing I'm asserting on and the expectation. And this allows me, if something happens, for example, I change a tree node, Bond will immediately pop this up. I said, your test is about to fail, because it produces different things. And it gives me this diff. And in this diff, I can see exactly what things are different. So instead of data 4, I have data 7. And I have a new left node where data 6 got pushed. Okay? And Bond will ask me, do you want to accept these new observations as your new reference? And I look at it and say, actually, I expect this, because I've changed the tree. So I expect the shape of the tree to be different. So I press yes, and then the new file gets saved as reference for future runs. So with one keystroke and some thinking, it's as if I've edited all those assert equals to match the new values. And now these become the new reference. Or I can press K, and it'll pop up a code merging tool. It's a visual tool. I use KDiff3 for my Git merging, and this is exactly what is here. This is the reference value. This is the current value. And now I can use all this user interface for every place where my reference is different from the current. I can say, I want to keep the reference for this place, implicitly saying the test is bad. I mean, the test has failed. This is the correct thing. Or I want to keep this, meaning for this particular line, I want to change the new reference. So this allows you to kind of either to go line by line, difference by difference, and say the test is bad here, or the test, the new reference, the new expectation should be updated. Or you can press a button and say accept all new, or accept all old ones.
George?
Yes.
Well, it seems that you need to run this test once, at least once, for the first time to generate this JSON file, right? So you need to be sure that your first version is correct with works.
Yes.
Binary search tree. What if it is wrong?
Absolutely. But you see, just think about the timeline of the long project, okay?
Yeah, the long run
When I first run the test, I'm invested in it. I'm actually committed to check that the test ran correctly. What I want is in the future, I want very quickly to verify that it's the same run. So yes, the first run, you have to read this and make sure it's correct. Not only the first run. Even when you do maintenance and you see a difference, don't just quickly accept the new changes. Think about it. Okay? You may have to debug. You might have to figure out.
Maybe you're going to cover it later, but this type of test really covers the content data itself, right? When you run versus canary data through the system, the data could be changed. You may want to maintain the structure or the integrity of your code. But this is more data-centric, so you're going to cover the other aspects?
No, not directly. I think what you're getting at is this test really is good. This is really assert equals.
Yes.
Okay. What you assert on, though, it's up to you. You could write. So on one hand, I work hard to make my test deterministic. So we'll talk about mocking time, mocking everything. So all my tests run as of February 22nd, 3 years ago in Touchstone. I picked a particular date, and this makes all the dates the same such that I can compare. Some things are not really expected to be the same, right? Then I only observe things, perhaps I take my data and compute some sort of structure from it. and I observe the structure. Okay, so you have to think how you use this. And there's some tricks.
Sorry. This example is a tree, and then it's actually have a tree which has two elements down the stream, so it's good. But because of the fact that JSON does not have order stored inside it, how about if a tree that one node has multiple nodes, and then the order actually is important for those?
No, JSON has order, actually. Well, actually, this is sorted JSON. So there is an order here. If you have arrays, obviously they have order, but dictionaries are sorted here. Sorted and indented. Just try to make it easy to read.
George?
Yes.
Two questions. One of them is, so how does one actually know what is the internal data structure of the tree to put into JSON? Do you just work with the properties?
Okay, the question is, how do you know what to spy on? Most often, I write my spies, I don't spy a whole tree. Most often I say, spy the value of x, y, z, blah. And those are arrays or numbers or strings. If I want to spy a data structure, I sometimes write serialized.
Yeah.
So I say, okay, I care about this fields, and this fields.
Okay.
Bond will use that.
Okay. The second question was actually, with the first way of writing tests where you have all this list of assert equals, I mean, the good thing is you can write your test first and then actually implement your tree until it passes, right? But with Bond, it's not possible because actually, even if your tree just returns nil, like an empty array, your test is going to pass with the first run, right?
Yeah, so that's a very good question, but I think it's not a problem actually. So Matt's point is that in test-driven development, you write the test first, including the setup, exercise, and the assertions, and then you write the code. And that's fine, but that's not how I do it. I find it too hard to do it that way. The reason is that I can write this first, but very often it's very hard to predict exactly how it's going to look, because I would have to kind of run this by hand in my head to find out exactly how the tree is going to look. So what I do, I write the first half of the test, okay? And then actually I say I spy the tree because I know I'll need to assert something on the tree. I just don't know exactly what the tree is. Then I start writing my code. I go with the debugger. I verify this. And when I'm satisfied, I actually save the tree. So it's achieving what you're saying, except I don't write the test first because actually very often I end up copying and pasting from the debugger to the test to write the assert equals, if I'm talking complex code.
And we should also point out, like, the mechanism is that Bond, for the very first time for a brand new test, will default to a failing state until you explicitly say, yes, this is my reference. So it won't automatically assume the first output is the reference. You have to tell it. Okay.
Yeah,
but I think there's one way where I can manually write the tree, right? So as basically the previous one, the example George given, which is basically you write about 5 statements manually. I can manually write, instead of writing 5 assert, I write 1 expected result and then use that to compare so that you have an initial state.
You could write the JSON by hand.
But there's no. Okay, Bond will do this for you, actually. So to elaborate on what David said, pointed out, the first time you run it, it says there's no observation, and now you have all this. It's going to say, I'm going to fail the test unless you tell me that this new observation is correct. So it's not going to automatically go into passing state. You have to inspect the observation. Essentially, it writes it for you. Okay, let's move on. So for those of you who like sequence diagrams and want to understand exactly what happens in details, can you see from the back? You can't? Well, I should move here closer then. Okay, so essentially what happens, this is your test. This is the system on the test, the thing you are testing, and this is Bond, and this is you using Bond. So first, in the test preparation, I didn't cover it, but you really have to initiate Bond. You have to tell Bond, I'm in testing mode. Okay, so record everything. Then you're going to be spying. You've seen those spy calls. Those go to Bond, and Bond remembers them. But there's spying also, you will see in a bit, from the system on the test. So these are the indirect outputs that we mentioned. What's important with Bond, at least for what I showed you so far, is at the end of the test, what happens. So at the end of the test, all the observations are saved in a file, and it looks if there's a previous reference file. And if there isn't, one, or if there's one and it's different than the current one, it's going to invoke this interactive merging tool. By default, it's going to use the console. It's going to print a diff on the console and expect for you to press yes, no. If you press no, the test will fail. It won't update the observation, it will fail. Or you can invoke these interactive tools. They'll pop up a screen. And so, any questions about this part? This kind of half of bond. I'm going to move on to the main. No. Okay, so
I got a question
yes.
regarding this comparison. Does this comparison rely on the Git system, and the previous test result has to be added to the Git, or what's it?
No, the comparison is done with diff. No, Bond doesn't know about Git.
Okay.
The comparison is done with diff or kdiff3 or whatever visual diff tool you have. The reason why you have to save the observations in the repository is that when your colleague checks out the code and runs a test, they want to run them against the reference.
Exactly.
So the reference has to be traveling with the code.
So in case of any continuous integration system that checks out the latest version of the code, it needs to have reference files.
Yes. So we, as a matter of fact, we do commit the observation files with the code.
That's actually really powerful because then, let's say you have a code review, someone can see the change that you made and also how it changed the test and also what it did.
Exactly. So you'll see soon that if you put enough spy points, the observations end up being a log of your run. So you can open the observation and see exactly how the code runs differently than before.
It oftentimes is many more lines than the actual code you wrote.
Yeah, we have observations that are 1 megabyte long.
Yeah.
One problem I faced with this kind of testing is that sometimes there is conflict. The test cases are too big, and someone has not updated the test case. Then there are conflicts, your changes and someone else's changes. Then it becomes a problem.
Well, that can only happen if somebody makes a change to the code and doesn't run the test and commits that.
Considered a failing test.
Yeah, but that's a process we're trying to avoid,
You can
right?
catch that in code review.
And that's also still true of like vanilla testing as well.
It's not easy to find out that something must have changed unless you run it on Watchtower and you realize that.
No, okay, these run very fast. Okay, but the same would happen, as Davis points out, if you forget to change the assert equals.
It's the same with the regular testing.
With the regular testing, if you forget to change the test, yeah. This hasn't been a problem so far for us because we do run the test every time before we commit, and you'd notice that something is different. Okay, so I want to talk some more about a more powerful form of testing. What I showed you so far is state-based testing. You run your code, and then you go grab its state, and you do assert on the state. Okay, and that's good. But you're missing all of the interactions that have happened with the outside world. And sometimes the end result of the test, the end state may reflect all of the interactions, but in a very indirect way and very hard to debug. If the end result is different, you don't know, is it because different things have been written to the database than before? Is it because there's a calculation error or what? And that's why people are moving, actually, to something called behavior-based testing. You might have heard of this. It's kind of growing out of test-driven development, behavior-driven development. This is a more powerful of testing, but really all there is instead of checking, instead of worrying only about the inputs I give to the code and the state at the end, I'm also checking the behavior of the code, what it does to the outside world, for some definition of outside world. Let me show you this in a diagram. So this is the code we're testing. It may be the session summary update. Okay? This is the dependent on component. This is perhaps the database or something else that is being used here. So what we're going to have to do is pass these inputs, and we'll assert on the outputs. This is state-based. But we're also going to be asserting on the output, indirect outputs of the code. And we're going to be, a little bit later, maybe in 10 slides or so, we'll be worrying about what kind of indirect inputs to tell this collaborator to give to our codes. Essentially controlling these as well, using mocking. I use this a lot. In fact, this is what makes testing a lot more powerful. For example, we write a lot of code that's very rich in interactions. You want to know not only what's the end result of your computation, but what HTTP requests were made in the process, with what parameters, and of course, what came back. What database writes were made. So for example, in Touchstone, I intercept all the writes to the database, only the writes. And I save them all in the observations. These give me a trace of external state changes. So a test may fail even though it computes the right answer, but it now has 10 database requests instead of 1. And if you use Django, it's so easy. It makes it seem like easy to write code, but it ends up generating a ton of database requests when it shouldn't. My test will fail. What shell commands are executed? I care about that because that's all part of the output of my test. Okay? And this is the code we write here at Conviva. We don't write sorting routines. We write code that does some calculation but does a lot of interaction. So we have to do a lot of this. Okay? So let me bring back the diagram from before. So we had bond where you started, and then these spy requests, these are from the test. This is spying from the test. This replaces assert equals. But bond can just as easily do spying from the system on the test. These you couldn't even write with assert equals. This is in the middle of your code. Just before you send an HTTP request, you're spying the request for testing purposes. Okay? This will allow the test to indirectly assert that you've done the request with the right parameters. Okay? You couldn't possibly do this with an assert equal. So this is already bond going beyond what we've done before. Yes?
What if the external call, well, actually, it's not an external call, it's actually an external library call. It's a functional call where basically, how do you capture those?
Yes, the question is, how do you do this? Is that? Okay, I have a whole set of slides going next. Other questions about this? Okay, so I'll show it first with bond, and then I'll talk some more about dependency injection and mocking in general, because bond is not the only spy in town, obviously. So I'll show it for Python. Let's say that this is part of your production code. It's the code that you use to make HTTP requests. It's called make request. It gets a URL, maybe some data. If the data is null, it's a get request. Otherwise, it's a post request. And here you write your production code. This is the actual code. The first thing I want for my tests that every time an HTTP request is made, it should be recorded and observed and implicitly asserted in future runs. Okay? All you have to do in the Python library for bond is put this annotation, declare this as a spy point. And this will do many things, you'll see. But the first thing you will do, it will automatically insert right at the beginning of this function called a spy of the URL and data. Okay? And then it will do more things later, we'll see. Okay, so this is one mechanism bond has for actually spying in production code. But I want to point out, until now I showed you test code. Now this is production code. This actually goes inside your production code. So you have to think, what do I want to observe, what behavior I want to test on, and you have to go make some changes there.
Sorry, just one question. So another way is that we can actually go to for example, if the DOC is actually a mock, then we can go to the mock and then expect result from there instead of.
Yes, indeed. We're going to talk about that. But either way, you're going to have to somehow do something in your production code to use the mock. Okay? So that's called dependency injection. So this is the way bond does it. I need to point out, so you'll be using bond in a hands-on project at the end of these lectures. For Python, there's this spy point. For Java, we couldn't write this spy point in time, so there's a slightly uglier mechanism for Java for now. I use these spy points a lot in my code because, again, we're not writing algorithm-intensive code. Our code is full of interactions, and those are just as important as the results of our algorithm. So, for example, in Hermes, the Hermes installation scripts use bond for testing. The end result is not something easy to assert that at the end of the installation something happens. It's much more important what commands were run, with what parameters, in what order. So that's all achieved by spying on shell commands, for example. And if I run the test later and something happened, like one of us makes a change to the installation script and suddenly a command doesn't run, or another command runs, or it runs with different parameters, that's something I want to know about. Maybe I need to update the test, or maybe I call it a regression. Okay? So generally, I spy all the uses of external APIs. All the state changing writes to the database. And this is how your file ends up being 1 million lines, or not 1 million lines, 1 million bytes long. Okay? All the HTTP requests I spy, all the shell executions. I want such that when I run my test, I want it contained. I want to know what it does, not just to the data structures, but to the rest of the world.
Yeah, you showed us how to use the spy with decorators, and decorators in some sense add some overhead intermediate layer before you call this function. You said that it was a production code. Is there a way to disable this spy at some point without changing the code? Flags or something, or how much is the overhead?
Okay. Yeah, so the question is the overhead of this. So if bond is not started, this is going to be a very fast thing, but it's going to be an overhead. Okay? It's not something I truly worry about. The moment you write Python, I shouldn't really be worried about that kind of performance loss.
So inside of the decorator, there is a kind of...
There's a conditional.
Yes, a condition.
Yeah.
If it is not initialized, then it directly calls this make request,
Yes.
otherwise it keeps
Yeah.
trying.
So it bypasses. Now, there are mocking libraries that do dependency injection at runtime, using reflection and using bytecode editing at runtime. If you've heard of Aspect J, stuff like that. Those, the way they work, will actually modify this code when in testing to inject this. Okay? So we don't have that for Bond. That's quite a bit of implementation work, but that's possible in principle. So moving along, I kind of skipped a few slides. I'll post a slide somewhere you can see. But I really want to move on to testing with doubles or fakes or mocks or whatever, because then we're going to bring this testing to a whole new level now. And Bond will stay with us. We'll see. Okay, let me just review. As you can tell, this was meant to be a separate lecture, so I need to wake up my students typically in the morning and review a little bit. So we have the system under test with a bunch of collaborators or dependent on components. And so what can these be? If you're doing a unit test, maybe the system under test is a method. But if it's an instance, and you may think, oh, this method has no dependencies. Well, if it's an instance method, the constructor is a dependency, because you need to run the constructor before you can run the instance method. Even though you're not testing the constructor, it's a dependent on component. More interesting methods will actually make calls out to other components, so helper methods. If you're doing a component test, this is a component, then perhaps what you're targeting for testing is a bunch of methods and classes, but there are other methods and other classes in the component that may be needed. And even for integration tests, the dependent on components may actually be external services, like Google Drive databases, Conviva, portal authentication, all sorts of things. So if I have time at the very end of my lecture, I'll use the board to explain how I focus my testing in the projects I've done. But just to put it out there, I do relatively little pure unit testing, okay? Because very little I find of what I write are really methods that don't depend on anything, okay? So most often I do component testing and integration tests. But I set them up such that they are very fast, just as fast as a typical unit test. And they do a lot of assertions using spying that allows me to pinpoint the behavior problem to a particular unit. So I get the benefits of unit tests without having to invest a lot on scaffolding to run every single unit in isolation. I'll get back to that at the end, okay? Now, why are these dependencies bad, in case you're not convinced? Well, extra moving parts. More things you have in your tests, more things to break, more things to maintain. So you set up, tear down, maintain. But sometimes these dependencies may make your test slow. So it's expensive to set up. If it's a database, that's a huge monster compared to the code you're testing typically. Okay? It's a different process. You need to talk to it over TCP. you need to clean it up, and if you don't, test will fail and such. The more dependencies you have that run in the test, okay, the more you are open to test failure because of bugs, not in the code you're testing, but in the dependency. If the dependency is MySQL, okay, unlikely you're going to suffer because of bugs in MySQL. But if your dependency is some other component you wrote, you probably want to isolate that. So we'll use an example that I wrote for my students, but it's really inspired by Conviva. You'll see. It's a heat watcher. I'm not monitoring quality, I'm monitoring heat. Assume that you want to write something that monitors temperatures over time and sends alerts, has some alerting function. The structure of the code will be something like you have the main routine, which you can start, and here's going to be the onTick is going to be a function that gets invoked periodically by your timer to read the temperature, decide if a temperature is off limits, and then send an alert. There's going to be an alerter that knows how to send alerts, probably PagerDuty stuff, something like that. There's a temperature class that you use to read the temperature, and then there's a time-related class which does two things. It has a timer and gives you the time of day. So the way you start this is you start the time provider and you give it a callback to be called every second or every minute or whatever. And that's going to be this function here. And you can use it also to get time of day. And again, those of you who work on the client, they recognize this kind of picture. Okay? It's time-driven, so we have timers in time. We don't have temperature providers, but we have the monitor. We have the player, the streamer from where you read stuff. And then we don't send alerts, we send heartbeats. So this is really what Conviva does at the client side, and even in the back end. You can probably recognize this. But I also chose this example because it's somewhat extreme in how hard it is to test compared to how little code really there is in there. So here we have more testing work to do than actually code to write. Why is this hard to test as is automatically? Time?
Timestamps.
What about time?
Well, sequence of times and how often it happens. We depend on time of the day.
We depend on time of the day.
Conditions,
Yeah.
environments.
One of the worst bugs I had in the version 1 of Watchtower was every spring when the daytime changed, there was a bug there. I never fixed it because, it only lived for 3 years. So very hard to test time-related things.
Oh, it's non-deterministic, essentially.
Non-deterministic as well, right? Especially if you read the current temperature. But there's more. I'm not thinking hard enough.
It's too slow. Huh? It's too slow.
It's very slow, especially, if your algorithm is, if the temperature has grown this much in an hour, you don't want to run the test for an hour. But you're all focusing on this. What about the other components?
What about alerter?
What about alerter? You don't want to send SMS in automated tests, okay? What about temperature provider? I mean, is every developer going to have a temperature sensor? No. And how going to simulate temperature? So I think it's almost obvious that you have to mock everything here, right? So that's part of the reason I chose it. Okay, this is notes for students to study for the midterm. We don't need that. Okay, so we need to do something. And there's multiple strategies here. Strategy 1 is try to avoid using the dependent on components. So we're getting now into how do you actually design code, not how you write tests. How do you write code such that can be testable? That's why it's very important to think about the test and write the test while you're writing the code. Otherwise, you're never going to get this right. So some things you don't really have dependencies, like sorting routines, but we do very little of that once we're done with the interviews, right? In the interviews, always sort. After the interview, you never sort. Okay, so goal number 1 is we're going to have to try to massage the code, refactor the code to have more independent units. So this is how you would write the code for the main logic in this temperature watcher if you didn't think about testing. If all you thought about the code should have the functionality that your product manager wants. Okay? So you put it all in this onTick, and then you get the current time, and then you have some complex logic that reads the sensors, and finds out where the sensors are, and reads them, doing something like this get temp on the temperature provider. Then you have your complex decision logic to decide whether to alert based on the current readings and the past readings and the state. And then you're going to probably invoke the alerter, whether to alert or not. And then you're going to be done. And you actually run it on your desktop and it seems to be working. The problem with this is that what we have here, you intermixed interaction with computation. The computation is where most of the bugs that you're going to have. You're going to have some bugs in the interaction. Maybe you call the thing with the wrong parameters. Okay? But that's not what you want to test when you want to test this logic. You're going to test the temperature provider separately. Here you don't want to test that, but you kind of mix it in. It's very hard to take it apart. Okay, the first thing that you do is you have to write code that separates logic, where the bugs are, from interaction. Okay? And in fact, if you have an IDE, a few clicks of the button can actually refactor the code to get it to this state. So this is a very important slide. Okay? So stop looking at your laptop for a moment. I'm going to extract in this separate function a function that has no interaction, but all the logic. All the complex logic, if you have conditionals, loops, nested conditionals, they should all be in a function that doesn't do interaction. And the function, of course, needs data. I'm going to pass that data in. I'm not going to let this function read the time. I'm going to pass it in. Don't read the temperature, pass it in. Don't send an alert. Tell me what alert you would like to send. And then what's left in here, this is the onTimer function. This has all the interaction, no logic. I'm going to read the time. I'm going to read the temperature. I'm going to pass it in into this function. And I'm going to send the alert if the function returns an alert. Okay? So this is a very classic pattern in testing. It's called the smart code, humble code. What I was trying to say is that this is the smart code. This is the code that tries to be smart, and you're going to have bugs in. And this is the code that does very important stuff, but there's no room to make mistakes here. This is like, reads like pseudocode almost. Okay? This does all the interaction. This is called humble code. You could call it stupid code, but that's not politically correct. Okay? And the thing is, this remains hard to test, this code. So you're going to have very few tests for this code, but it's not as test-worthy. Okay? Not much is going to change here. It's not as much room for mistake. This is where I'm going to be making changes every train. This needs to be very testable. Okay? This is important. Okay? How you write code. Any questions? Okay? So if you see code that has URL requests, send URL requests in the middle of a complex logic, that's bad code for testability. I have another example that's going to be very familiar to people in the client team of a similar kind of nature. How do you kind of massage code to make it more testable? This is testing asynchronous interaction. And I wrote this kind of test, this kind of code and test quite a bit here a few years ago, and I regret it now. So I want to teach you what I've learned. Assume that we have this worker that is supposed to be running inside the thread. And this is the thread actual function. And this worker listens on a socket, gets work items to do work on. So it receives on the socket. Once you get something on the socket, it blocks here. You get something on the socket. You do some work with that message, and you put the result somewhere, and then you keep doing. So we kind of have this code whenever you have asynchronous code. This is very heavy to test. It requires running in a thread, okay? It's already much more complicated than you want in a unit test. Uses sockets, okay? That seems like an overhead for tests. But being asynchronous, this code has no way of communicating to whoever is invoking it that the work is done. So let me tell you how we in the client team used to write tests for stuff like this. You'd start the worker, which starts a thread, okay? And then that's going to take a little bit, but then you create a socket and you connect to it. So you connect it to the thread that you just created. You're sending a message that you have prepared, okay? And now what we used to do is say, well, we don't know when it's going to be done, so let's wait for 1 second, and then somebody says, no, you should wait for 2, and then somebody gets tired 6 months later and waits for 60 seconds. Because then, for sure, all the tests. How many of you have seen this kind of tests? Okay, yes. And then you wonder why 61 is 65, and then most of the 6 are going to be wasted, right? Because it all happens in a second, except a few times happens. Then you assert that the work was done correctly, which is hard typically because if the code was not written so that you can get the results of the work, and then you have to shut it down, and this may take a while, and then surprise, this test runs for 2 seconds. And when you have 1 test, that's fine. When you have 1,000, that's not usable. So here's what I'm going to do. Sorry, I have my alter ego speaking there. Okay, yeah, a few points I didn't point out. In some languages, you cannot sleep. So in JavaScript, ActionScript, there's no sleep. So this test becomes a lot uglier because you now have to break into multiple parts, callbacks, and such. Okay? And the actual solution is to go back, rewrite your code. Okay, so the same kind of humble method, humble code, smart code. I take all the code that does the interesting part, that has all the computation, and I separate it into its own nice little method that gets everything it needs through its parameter and returns everything it produces through its results. And this is going to be very complex. And I'm going to leave here the humble code, which is rich in interaction, very poor in actual computation. So I'm going to have here the threading part, the listening part, the loop, and then when it has to do something interesting, it calls into this function. Okay? So same story. This code has no communication, all computation. This has no computation, all communication. I'm not going to test this very much. I'm going to have 1 test with real threads, with real sockets, just to make sure things are connected properly. But I'm not going to try to use this code to test some complicated corner case in this. I'm going to just call this work function. So now, this is how the test looks. I create a worker. This worker, yes, it's a subclass of thread. So if I were to start it now, it start a thread. But I don't need to start it. All I'm doing, I'm going to be invoking its work method. So this is a worker that's really set up to run in a separate thread, but it can also be run synchronously directly. Okay? And then it returns the result. I assert the result is correct. It takes 2 milliseconds instead of 2 seconds or 60 seconds. Okay? Questions about this?
So I will go back to the previous slide. So sometimes when you read this worker class, you want to have this work method to be private in some languages.
Are you talking about private versus public methods?
Yeah.
Yeah, okay. I'm sure there are textbooks written about this. My personal attitude is that I'm going to bypass some of these privacy mechanisms for testability. I'm typically going to have more methods public than you should have if you don't think about tests. So I sometimes create methods and make them public accessible so that I can test.
And at least I know in certain languages there are tools to sort of make this easier. Like I think Guava has this notion of @visible for testing annotation in Java. So you make it public, but if it's used anywhere other than test class, find bugs will claim that as a problem, basically. Or it can even flag as a compiler warning.
Exactly. In C# you can put in the same namespace, right? So that you can use the namespace or something like that to make sure that in the test.
Yeah, I'm sure there are mechanisms like this.
Yeah, so there are tools so you can have it both ways.
Okay, other questions? Okay, so that was strategy 1. Strategy 1 was just trying to refactor the code to create fewer dependencies for the code we want to test. Okay, and there's only so much of that you can do. Sometimes really you can't separate it so easily. So one school of thought there is if you can remove the doc, use it. So sometimes I do write tests. Okay, sorry, go back one slide. I have this module 1, which sits at the bottom of my dependency graph, doesn't have dependency itself. I write tests for it, unit tests for it. Okay, this is my sorting routine. I write tests for it, and then when I write this module 2 that using my sorting routine, I'm going to let it use the sorting routine directly without mocking, if it makes sense. Okay, so I do actually quite a bit of this for modules that are computation only and no interaction. So that's why I said when I write tests, relatively few of them are pure unit tests because many of my tests include other units that have their own unit tests separately, but It's just simpler that way. So essentially what I'm trying to say, you'll see mocking soon. Mocking has a cost. Okay? I'm not saying that we should pay that cost for every module everywhere. You have to think, be smart about where you invest, because it's a real investment. Now, if you do this a lot, some of your modules at the top of your hierarchy are going to involve tests that actually invoke everything else. Okay? And that's going to make the test somewhat slower, somewhat unwieldy, somewhat harder to debug. But what I find is, and I actually have some of that as well, and I still consider them good tests, because as long as it still runs very fast, and as long as I have spy points in so many places that I can debug the first deviation from the previous run, not just the end result, because I'm now running millions of statements. The first deviation, I get the benefit of unit tests mostly. But sometimes you can't do this either. And what you're going to do then, that's where test doubles come in, or mocks or fakes. And doubles, as you may know, it's a highly trained replacement vaguely resembling the actor. And vaguely is important here. So test double is not a full reimplementation of dependent component. Okay? You can double a MySQL database with 100 lines of code for various scenarios. So it depends very much on the scenario. So how you write the doubles. And then the textbook that I passed around has a whole classification of what doubles may be. Let me just go quickly over it. Although I'll tell from the beginning, I don't put that much weight into this black or white classification. But generally, people like to say double is the generic notion of a replacement. Stub is a kind of double that's actually very, very stupid. All it does, it has some pre-programmed inputs that it gives whenever it's called. Okay? So essentially, copy and paste stuff into your stub. I don't use stubs very much because very quickly I outgrow their capabilities. Mocks, people say, would be something that does what the test stub does, except it checks. Not only does it provide inputs when it's called, but it asserts that it's being called properly a certain number of times. So I achieve this with Bond spying. Fake objects, this is like the all-powerful double. And by the way, stubs and mocks, there are libraries out there for various languages that with just a few lines of code will generate this for you. Okay? And fake is something that you actually say, okay, I'm going to have to implement my own implementation of GA Producer for testing purposes, doing very little, very fast, just so that I can run everything else that depends. So honestly, this is where I spend most of my investment in testing.
So there are simulators that kind of could listen to the interaction, actually dynamically build some sort of a fake dependency. What's your take on those?
Yes, I think you're talking mostly. There's many ways, many libraries that try to automate this for you. There's record replay libraries that will watch you run the thing and then will try to simulate that. My take on that is that every time I try to use them, I outgrow them very fast. And then it becomes frustrating. So if you use frameworks like Rails, for example, Hello World, you type one line, it produces 100 files, and it works. Hello World. The moment you start to do something serious, you have to go in, understand those files, understand how to make it not be so smart, to do what you want. So I generally bypass this. I bite the bullet and go directly to implement my own, design properly for my needs. And because of that, I don't do it everywhere. I think carefully where I do it. So I'll talk about fakes for a little bit. So a fake is a handwritten, meaning that you actually have to type that code. It's not like a library going to create it. And implement some functionality of the doc. And this is very useful when you don't have the component yet. It's very useful when this is across a major interface in your system. By the way, we have fake implementations. Can you give some examples of Conviva?
We have some fakes for the LCG so that we actually use it for the testing of other systems.
Right.
LPSIM.
LPSIM.
Oh, yes.
Right. The client team has a fake backend. Touchstone, in a sense, is a fake for testing. Touchstone has its own simulator, its own LP sim. So we have written these. So it's not really a surprise. The question is, how do you do it systematically? I generally, in all my newer projects, I try to have fakes for my databases and web services, because those are actually very, very slow. So it's a significant investment, I agree, but it's something that if you start day one, it's a small investment day one, you'll have to incrementally grow it as you grow the code. At the end of the project, it's going to look like a significant piece of the project, but if you build it incrementally, it's really not a big deal. So let's go back to temperature and alerts. See how we can fake it. So first we want to fake the time provider and the temperature provider. Timing is actually one of the most fundamental notions in many programs, time-driven programs. And it's one of the most impediments to testing, like quick testing. Yet it's one of the easiest to fake. What you need for a time provider, you need to fake the time it returns. So it's just going to return a preset time. And the register on ticket is pretty much the same. The other part of all fakes, so the fakes, let me step back. The fakes typically simulate the interface of the object that you're faking. But they also have a configuration interface, which you don't have in a real time provider. So the configuration interface, look at this, 4 lines of code. This does amazing things. What this does, it sets the current time to some start time, and then it has a loop that increments the time by 1, say 1 second, and it calls all the register handler for the time. And if, with these 4 lines, you can simulate a lot of the time-driven code. We have this kind of time fake for our clients. And this allows us to actually speed up testing, because instead of waiting for 1 second to pass, you increment the time such that everybody asking for the current time will see that the 1 second has passed, and then you call everybody who has registered a handler. And once they're all done, there's no point in waiting for the second to pass. You can increment the time and move on. For example, imagine you have client code that says sleep or wake me up in 20 minutes. We have something like that for expiring something. Okay? If nobody else has registered a handler for anything in this 20 minutes interval, this loop is going to be a no-op going down for 20 minutes times 60 seconds, and then it's going to invoke the 20-minute handler. So when you build this, it's amazing to see it run, because the test that used to run for 20 minutes now finishes in a fraction of a second. And that your code couldn't tell that it's not using the real time. Okay? So this is the first thing I mock in all of my projects. So for example, in Hermes has some time-dependent tests. Okay? There's a time marker. We can tell it simulate Hermes at midnight, or 1 minute after midnight, when we know that certain files change and we have to do the right thing. Questions? Yes.
So in a lot of languages, time is sort of statically available, right? It's something that's very easy to sort of skimp on doing proper dependency injection for time. Are there some good common patterns that one can use for ensuring that you properly inject unmockable time?
Yeah. So the point is that in some languages, the time is like almost like a keyword in the language, so it can be anywhere in your program. I don't have a rocket science answer to that. So what I do, because knowing that I'm going to be mocking time, I'm very disciplined. I always call my time provider to get the time, even though there could be another keyword that does it.
Another question regarding this FakeTimeProvider. You essentially create a new class where you replicate some of the functionality from the original time provider, right?
Yes.
Instead of this, probably if you use abstract interfaces and then have different classes that realize that interface, or through inheritance, you can still use some of the functionality from the original class. For example, this register on T. Yes.
Absolutely. Yeah. So use
then
your language.
You test more of the original time as well. Right?
Absolutely. So use your language. Use abstract interfaces. you may have the FakeTimeProvider inherit from the real one such that you don't have to write this code and you can reuse it. All that is fair game. Okay, so faking temperature. Okay, well, how are we going to fake temperature? Here you have to sit down and think, what kind of fake temperature will I need to test my code? You don't want to simulate real temperature changes because that might be too much. So what I've decided, let's say for these algorithms, is that we need to simulate temperatures that are functions like this. You start at a certain temperature, you increase at a certain rate, and then you stop at the max temperature. Because I know what kind of functionality I'm trying to test, and this is going to be enough by varying the levels and the slope, it's going to be enough to test all of my code. Okay? So you write just this. And if you've seen the example in the bond page, it kind of follows this. So this is the temp provider interface. As I said, the temperature provider has to look like a real, the fake temperature provider has to look like the same like a temperature provider. So it has to have this interface, but it gives you a fake interface, fake temperature. And then this is the part that's really faking it. And again, it's only 4 lines of code. So what it does, it's pre-programmed with a start, an increase rate, and an end temperature. It remembers those. It registers itself with a time provider, such that the time provider every second will call this fake temperature provider to let it increment the temperature until it hits the rate. Okay? So just a few lines it could be. What I like about this kind of testing is that it allows you to be creative. While perhaps writing the alerting code and reading the temperature is boring code, so sometimes the production code is boring. There's a lot more beauty sometimes in the test code. So when people tell me I don't like to write tests, well, sometimes tests are more interesting to write than the code itself. You can tell I like. There's a lot more room for creativity sometimes in writing these fakes than writing the real thing. The real thing, a product manager has specified.
George,
yes.
so just say a parallel. In the content world, they call it advertisement creative. So the real creativity is in the ads production, not.
I see. Well, but there, the ads, most people would say, okay, I want to work in ads because that's where money is. But in testing, I often hear that.
They actually use a word called creative. Specifically say ads is called creative.
That's creative. Yeah, testing is creative, sometimes more than the production. Okay, so databases. So we use databases a lot here at Conviva, but in many cases, I don't think we use them properly. I'll tell you why. In Django, those of you using Django or Rails, the framework forces you to use the database in a certain way across an abstraction. Okay? If you don't have that framework, you end up sprinkling database calls all over your code. And then this story is not as strong. But if you have a good abstraction for databases, when I started writing the Watchtower tests, one simple test took 5 seconds. I thought of it as a unit test because it was testing some insertions and some deletions. But setting up my SQL, it's a big monster, separate process. Erase all the data, recreate the table, start populating, 5 seconds. Okay? But I take advantage of the fact that I have an abstraction that's SQL queries. In fact, it's even a higher level than SQL queries. It's one configuration line change in Django to say, if I'm testing, use SQLite 3. Because most of the functionality will be the same. 150 milliseconds, SQLite 3. Okay? Still running SQL queries. What I do in Touchstone, I actually bite the bullet and I wrote my own abstraction, even higher level, that allows me to replace the database with a hash table, in-memory hash table. Okay? So 10 milliseconds, the same test. Okay? And really, my code cannot tell that this hash table is not as good from a point of view of storing data and reading data as the real MySQL monster. But this requires an investment. Okay? So for something like a database in Touchstone, I know I'll be using it a lot. This speeds up my tests. I can run them in a minute as opposed to an hour. That's a big difference.
So I remember we did this when we back when we worked in Portland. There was an important cases where using SQLite 3 So you miss certain cases where certain queries would be fine and SQLite 3 would be a problem against traditional SQL data.
Absolutely. So this is not free.
Yeah.
Okay. SQLite 3 and in Watchtower too. In Watchtower, I have a test that has to run on MySQL because the abstraction that Django gives me is not perfect there. And sometimes you learn that the hard way. But I still run most of the tests in SQLite 3, some in MySQL. Just like before with the asynchronous code, most of my tests bypass the threads, but I have one test, two tests that test the threads in some corner cases that bit me in the past. How are we with time? Getting hungry? Hungry for knowledge? Okay. Okay, so, well, I guess this is just a little bit repetitive. The database is one of your most common and heavier dependent on components. So think hard about it. Write code that allows you to replace a database with SQLite 3, for example, for most tests. And this is one of the best reasons why people use frameworks. Generally, I don't like frameworks because they kind of tie my hands, don't allow me to be creative. But a good framework will come not just with constraints, but with tools. Because they can build a tool for Django because many people will use the database in the same way. So it's worth the investment for somebody else to provide the testing framework. For Conviva, if we don't use a framework, sometimes we have the discipline to design a framework in there to allow us to use across multiple projects the same kind of, to leverage the same kind of infrastructure. Okay, so along the same line, where do you put mocks? Okay, there's a notion of seams. Seams is a place in a, so if you imagine a system, most parts are tightly connected, but if you know the system, sometimes you see a kind of loosely connected section. Yeah, teenagers only call in the worst possible moments. When you want them to call, they don't. Okay, so you have to think hard about the systems that you're building. Where is the seam in my system? Where is the part that's more loosely connected? Because that's where you want to inject your double. You want to inject where there's loose connections because it means the double has to resemble only in a few ways. It doesn't have a rich API that you have to fake. So some of them are obvious. Between a client and the server, you're already forced to have a loose connection and the protocol specified. So we normally write fakes there. We have LPSIM, fake clients, we have fake backends, and we actually do this. But again, if you use a framework, this is all within a backend. If you use a model view controller framework as opposed to big mess that you invented in a moment of creativity, this prescribes a certain interaction that allows you, that essentially forces seams in your application, which we want to take advantage of. So what I have next is something that I'm going to be skipping, but let me just give you an overview in case you want to see. This is for the students, which all write projects that have very little computation and no loops whatsoever. All they do is calls to Facebook, Google, and Dropbox, and LinkedIn. And this is the project. It's very rich in interaction. And they end up writing code like this, where they hard code in the middle of their application some URL to Dropbox to read a file, and then some testing, some checking of the results. Okay? And the point of the next few slides is how you could, if you start thinking about testing this code, well, suddenly it becomes a lot harder. Because yes, I can use Dropbox in my production code, but in testing, I don't want to have an account. I don't want to delete files in Dropbox. So it kind of forces you to put abstractions in. If you don't think about tests, this is good enough. And you can release it and call it done. But told you the story about the changing oil in the car. Let me just move on about this. But there's a sequence of files where I keep massaging it and showing how to fake. And the more you massage it, the simpler the fake. So typically, if you choose the right abstraction, the fake is going to be simple. And the right abstraction is useful even if you don't think about testing. The code will be cleaner too. But testing just keeps you honest. Let me skip this. Okay, so a few more slides, and then food. So what we looked at unit testing, asserting, and then I injected this stuff about spies and bond. Then we look about the whole world of faking, and we talked about how to write fakes. What's left is one very important detail. How do you get your test to use the fakes while messing up your production code as little as possible? Right? Because the production code has to use the real database. In testing, suddenly has to behave differently. So this is a whole topic, and it's called Dependency Injection. And there are libraries that people have written. Have you heard of Juice? Google Juice? That's one library, and there are others as well. And Bond, surprise, does dependency injection as well. But before we even go to using libraries to do your work, it's important to understand how you write code such that it's easier to inject mocks. So going back to our alerting on temperature, this is one way you may write a bad way to write your main method. Let's say that the constructor, you write it, you design it such that it needs some expensive to obtain object, maybe a connection to some PayPal or whatever. And then in the constructor, you're constructing these collaborators, which themselves may involve complicated constructions with expensive to set operations. And it may seem, if you don't think about testing, this is a natural thing to do, because you want the constructor to get your object ready. So you want the constructor to set up all the connections. That immediately forces you to have the constructor mess with all the collaborators. So it makes the constructor very heavy. Okay? So it's not good to construct the docs, the dependent components in the constructor. But it's even worse to start using your collaborators in the constructor. Normally I construct them in the spirit that, okay, let's get the system ready, I'm initializing them. And that sometimes it's complicated. You may even send an alert, saying, okay, I'm started and all that. Why is this bad to put so much stuff in the constructor?
You cannot mock the input.
You cannot mock the input.
You can't mock any of your dependencies. It's sort of all fixed in the constructor. It's hard to control or change implementations of those.
It's hard to change implementation of those, yes. I want to get something more. It's hard to decouple. I think it's the same spirit. I have something simpler in mind.
You can't control the lifecycle of when they'll start. So when you create the output, it's independent of the clock.
You cannot control the life cycle, yes. What I had in mind, this is all true. Right?
So I think it's a static, not dynamic.
Static, not dynamic?
In terms of like, when you cannot dynamically create what you want to create between different scenarios.
No, you can. You can put conditionals here. You can do dynamic.
You have to change the code. Production code.
Yes. Okay, let me just say what I had in mind, because trying to guess you what I was thinking of didn't work. The problem with the constructor is that it's a dependency that most of us forget for all of the instance methods. You have a simple instance method that does a little computation. You cannot even invoke it without constructing the object. But the method itself doesn't need an alert, it doesn't need temperature, maybe it only talks about time. So the constructor is a very important piece of dependency, because you cannot run anything else without having a constructor. Okay? Even if you have methods that otherwise would be perfectly testable. So don't put so much stuff in the constructor. But the first thing, actually, one other way to get around this is, if you can make your methods static methods, they don't need a constructor. You remove the dependency. So if you see a method that doesn't use this or self in Python, you should think about making it a static method. It's easier to even think about it. It doesn't need an object, doesn't have access to an object, cannot mess an object. It's an important abstraction. But there's only so much of that you can do, right? So what you do instead, I have a few techniques here, but in the interest of time, I'm going to speed up a little bit. I'm going to construct the collaborators. Okay? However, I'm going to take the mindset that all constructors do very little, just initialize some variables, no talking to the outside world, no writing to the database. Okay? So this constructor initializes some variables, constructs these objects which themselves don't do anything. And I move all the starting code in a separate method, a start method, or maybe even several start methods. This allows me to construct this object, call my methods that don't need all of this stuff, but only start it when I truly want to start it. Okay? I didn't appreciate this when I started writing code a long time ago, because this is part of construction conceptually. Yeah, but it brings in too many dependencies. You are tempting us with food. That puts pressure on me. I want to skip a few slides because I'm hungry. Okay, I want to skip to dependency injection with bond. And I'm going to show you two ways in which bond can help here. So one of the ways that we ended up using bond quite a bit to inject dependencies is something that will make some of you cringe. We sometimes write in our production code like this, in Hermes, in Watchdog, in Touchstone. If bond is active, meaning that I'm in testing mode and bond has been initialized, then I do two things. First, I call a spy. This will have the effect of telling me I've gotten here with these particular values of the variables that I'm spying. But also, you will see that bond can be active, not just passive, passively observing stuff. That's bond that I showed you before. Bond can actually return things to you. And that's half of the power of bond. And the way I've written this code, sorry. Okay, so now I crashed my phone. Okay, so this is a way of mocking, of injecting mocks. Essentially, instead of this production code, I'm gonna do whatever bond says. Okay, this has.
Do you want to take a break?
Well, now I'll call her back in a few minutes, but I need to stop this. Okay, so sorry, let me go back. We've talked before about spying and mocking at the level of a method. An entire method gets taken out of the run and the result replaced with something that your mock says. This is useful for when you want to mock a little line in the middle of a method and you don't want to refactor the code to make this a method. Okay? So it's really a band-aid of sorts. The alternative, more elegant, is to take the code that you want to mock, for example, the make request, and make it refactor it as a separate function, and then put this annotation to say, whenever you get here, observe the arguments, and ask bond if it wants to intervene and provide a result. If bond provides a result for make request will be bypassed, the actual code. And the way this is done in bond is by deploying agents. Okay, so this is a new aspect of bond that I'm showing you. So you've seen bond spying. These spies by default are passive. They just collect stuff, save it, compare it later. But you can pre-program bond to say next time you're spying a make request and the URL ends with books, spy that, record that call, and give it back the status code and this mock result. Okay? So bond, or similarly, I can deploy another agent for the same spy point. Say if the URL contains books 100, it's reading a particular book, then say 404, not found, and some text. Okay, I'm simulating errors. So bond essentially has an internal state where it stores agents that you deployed, and the agents are just sit there until the code gets to the spy point for that agent. And then bond says, okay, do I have an agent for this spy point? And if I do, the agent can tell me to do a variety of things. This is how it shows in the diagram. So in the setup stage for your test, you are deploying a bunch of agents. You're pre-programming bond to respond in certain ways to certain spy points. And then you start making your code, running your test. You call the code. The test now calls the collaborator, make request. And make request has been annotated to be a spy. So make request will spy its results. So you get this automatic checking of indirect outputs. But Bond will also look at that point if there's an active agent for this invocation of make request. And this, you are allowed to actually put conditions on the parameters. And if there is one, it's going to return a response all the way. It's going to bypass the actual collaborator. It's going to return a response all the way to the system under test. Okay? So we use this.
How one knows the context, whether this run in the testing context or in production?
I missed the beginning of your question, but this only does something if you're running in testing.
So at the beginning of every test run, you should call start test, which sets an internal state variable so that it knows all the spy points are active, essentially.
So Bond is safe to run in production. It's a no-op. I mean, you won't spy. You'll just call the actual production code. And then at the end of the test is the same usual save observations. Okay. So I said that I'm spying I'm intercepting every write of the database. I intercept it, and I actually spy it, but I don't mock it. I actually use a mock database to return the result. For URL requests, I spy them, and I mock all of them, because I don't want to be touching the external services. Okay? So Touchstone uses Conviva, uses Portal, uses a bunch of other services that we have. All of them have mocks. I've written mocks for all of them. Only the parts that I need. And so what else can you do with bond agents? Bond agents have late binding. This is very important. You specify the spy point in code, but you don't put in the code what you should do when you hit the spy point. That is specified in the test. Okay? In the test, you deploy an agent that configures bond for that spy point. And this binding is dynamic. At runtime, bond will match agents with spy points. You can have multiple agents for one point. The last one that's deployed takes priority. Each agent gets a chance to decide whether they want to act or not. The first one that acts is the agent in charge. Bond agents cannot just return your pre-programmed inputs, although that's what we do most of the time. So what we do, for example, we put the spy point, we run the test once, we let it hit the external service, we copy and paste the response, and then we put it in the test, say, next time you come here, serve this. That's the first part. If you do this a few times, you'll have to start thinking, maybe I need to write the code to make this nicer and all that. So bond agents can run code to compute a dynamic result or exception. Okay? And bond agent can also say, in this particular case, I want you to run the production code. I'm not going to mock the result. Go hit the external web service, and because we want to have a test on the web service. So in the hands-on project that you'll be doing after lunch, you'll be using Bond to do some spying, to mock some of the results, and it's going to be an application that Jonathan and Davis have suggested to me to use the Port Authority's REST API to find out where buses are in Berkeley at any given time. And of course, you don't want to do that all the time in tests, but you're going to mock all that, and you're going to test and find some bugs into this application. So let me just wrap up. I have a few slides about Juice, but maybe I think they deserve a separate lecture. This Juice is all the rage in certain parts of Google now for writing code that you can test. So to conclude, testing has a profound impact on design. Okay? So what I told you here is not just how to write tests after the fact, but how much better you can write tests if you think about that and you do that while you write code. And you should try very hard to avoid designing software that cannot be tested. And I guarantee you, no matter how good designer you are going to do that if you don't write the tests while you design the code. So